These are your video notes for lesson 1.5 on linear equations and arithmetic sequences. The goal of today's lesson is to tie those two ideas together. So we've been discussing already before today the idea that arithmetic is linear, geometric is a curve, and today we want to connect up the arithmetic being linear idea to the equation of a line that you guys remember from Algebra 1 and geometry. So we're going to start by kind of reviewing that idea, then we'll get into the connection as we go through the notes. So I'm going to plot a few points here, starting with the ones that are in blue. And so clearly we've got a line. I'm going to throw that line in there. So some questions would be, if we were going to do the equation of a line, like what's the slope? Slope we can get by counting, so we can count up 3 over 1 and up 3 over 1, so we know our slope is 3. Pretty simple, right? Y-intercept is the place where the graph crosses the y-axis, so that would be at 0, 3. If I'm just going to say as a number, where is it at? It's 3 also. And the equation of a line. So to do our equation of a line, we have to remember the equation of a line, y equals mx plus b. So then from there we can go ahead. So our equation of y equals 3x plus 3. Okay, let's tie this idea together with the idea of an arithmetic sequence. So remembering our recursive rule for arithmetic, so we've got a starter term and we've got a formula, recursive formula for the sequence, which says previous term, remember that's just a symbol, previous term plus 3. So if we start generating terms and we're starting at our first term, our 0 term being 5, and we'll plot our points as we go. Now add 3, so add 3 and add 3. And again, we're seeing the image of a line, so we can say that arithmetic sequences produce a line or they're linear. Now the idea is, what is the slope of this line? Well, by counting, we actually have a slope of up 3 over 1. So we've got a slope of 3 again, the common difference here. Turns out if you go back and check out our D is also 3, so the connection. What is the connecting idea? Well, slope and common difference are the same thing. So we can say the common difference is equal to the slope, or if we're using it in terms of symbols where D is common difference and M stands for slope, that D is equal to M. Now also there's the idea of the y-intercept and how it's related to the sequence. Well, it's the starter term, right? I start at use of 0 and that produces, and that's, 5, so 0, 5 we consider to be the y-intercept also. So the use of intercept, the use of 0 and the y-intercept are the same thing. So symbol-wise, b from mx plus b is our y-intercept. That's the same thing as use of 0. So with that in mind, we can do some substitution here and replace m with d and b with use of 0. Now we're going to actually not give this as a format for how we write our equation of a line. We're still going to use mx plus b, but we're going to start to pull in this d and use of 0 as another type of form of a sequence rule. So we'll make that connection in just a minute. But first, let's just practice the shift back and forth. So give me the equation line, y equals mx plus b, if I give you the common difference and the use of 0. Well, again, I know use of 0 is b. I know the common difference is my slope. So essentially, really, it's just plugging in those numbers. So common difference, slope, use of 0, y-intercept. So given the terms given the information from a sequence, I can create a y equals mx plus b equation of a line that would match my sequence. This example just worked in reverse. So here is y equals mx plus b, write the recursive formula. Well, to do that, from here I would have to pull out what's my common difference and what is my use of 0. Remember, when you write recursive formulas, we always include a starter term, then followed by the actual formula itself. So things I want to jot down is what is d, so there's my d. What is my use of 0? That's actually part of the overall rule. And then here comes the formula rule, which is previous term plus 7. So previous term plus common difference. So in these two problems, all we're trying to do is have you see that transition from one to the other and what things are connected ideas, which are definitely slope and common difference and y-intercept and use of 0. Now, what we want to do with the d and the use of 0 kind of format is change it to another kind of rule. So recursively, when we do recursive rule, we say previous term plus, or it could be minus, right, some number. But recursive rules are generated by doing something to the term that came before it. Do something to the previous term. We're going to call this the explicit rule, and I'll explain what it means by explicit in a second. So now we're going to have two ways of writing a arithmetic recursive rule. One, recursively, with the d, previous term plus d, or two, explicitly, which is more of a formula based on the term's position. Now let's get into that idea. Like what's the difference between this and this? So if I'm doing it recursively, use of 0, star term, our rule says I should go previous term minus 2, so I'm going to subtract 2, subtract 2, subtract 2, subtract 2. Piece of cake, right? Let's sub in our information into here. So we know D common difference is -2, use of 0 is 9, and we'll create what's called an explicit rule. So how does the explicit rule work? So this substitution is no different than what I did in the previous slide. Like y equals mx plus b is dn plus use of 0. So here it is again, dn plus use of 0. We're just getting rid of the y and saying here's another way to generate the rule. Generate the terms by giving you an explicit rule. So the way it works is you actually plug in the term's position. So if you want the 0 term, if 0 is the starter term, you actually plug in 0. Well, if you take -2 times 0 plus 9, you get 9, the first term, or the starter term. You plug in a 1, you get 7, you plug in a 2, you get 5, plug in a 3, plug in a 4. So the way an explicit rule works is you can generate the term by plugging it in its position in the sequence. So let's say I want the 100th term in this sequence, I would just plug 100 in right there. -2 times 100 plus 9, there's my 100th term. Now, what's the advantage to an explicit rule compared to recursive? The advantage is if you need to go way out in the sequence, it's much, much quicker. If I'm going to do this use of 50 recursively, I have to literally sit there, in my head or on my calculator or whatever, and I got to subtract 2 like 50 times, or at least 45 more times to get out there from where I started. So that's going to be kind of time consuming and just sort of cumbersome to do. On the other hand, explicit, all I got to do is plug my 50 in. So if I want the 50th term, that n in there actually represents the term's position, right? So this is n, so is 2, so is 3, so is 4. So if I want the 50th term, I plug in 50. Well, a quick calculation, I've got 91, way faster than trying to run out there one term at a time recursively. So the advantage of explicit is you can go way out in the sequence much quicker. If I've only got to do 4, 5, 6 terms, then fine, recursive, no big deal. I can subtract 2 a few times, but that no big time waste there. But if I got to go way out here, then I don't want to do that. Okay, there's sort of a flip side to this problem, which is I want the 50th term, plug in 50, I get -91. This question says use the explicit rule, because again this will be much easier, to figure out which term is -177. So what that's saying is, let's say I'm at the 50th term right now, which is -91, and I keep going, blank after blank after blank. What blank would -177 sit in? Like, where is it? How far out is it in the sequence? So here what I know is I actually know the answer. I know what this is. I don't know how many terms it takes to get there. So what I'm going to do is plug in -177, saying I know what the general term is, I just don't know how many it would take, and now I'll solve that equation. A little bit of basic algebra and you're there. Now what that 93 means is -177 is the 93rd term in the sequence. So if we kept this running out to the 93rd term, in its spot would sit -177. So two different kinds of problems here. One, I want to find the value of a specific term. Here I know the term, and I want to know where it sits in the sequence. Okay, let's try one more and then we'll wrap it up. So star term, -5, my use of 0. And we're going to do use of 0 here because actually that translates better to like an mx+b. It translates better to an explicit. So we'll keep using use of 0 in this situation. Now, again, if I just got to go out for 4 more terms, adding 6, no big deal. Right? I can do it a couple times, but what if I got to go way out, which we're going to do later, then I don't want to do it recursively. The explicit formula, all you got to do really basically here is get your stuff squared away. So D, and then use of 0. So we do need to know this little formula. And then again, when I want the term, plug in 0, plug in 1, 2, 3, and 4. So I plug it in the term's position in the sequence, I can figure out its actual value. And again, the advantage is, let's say I got to go to 40, 50, 100, whatever. I don't want to do 40 one space at a time till I get out to 40. I want to just be able to plug in 40 in a couple seconds and I'm there. So 6 times 40 minus 5, 235. So in this sequence, if I ran it all the way out to the 40th term, this would be the number that sits there. And then the flip side of this problem is what term has its value of 139. So in other words, again, in this list somewhere is this number. We want to know what position is it in, which term is it. So then what we do is we plug in the actual number and we say n, which is location, or what number in the sequence is it, Is it the first, second, third, fourth, fifth, and so on term? And I solve that. So I do a little bit of basic algebra here, and n is 24. Now that means that the 24th term in the sequence is 139. Okay, and that sums it up for the 1.5 notes. It's kind of short. The main idea here is to connect the idea of an arithmetic sequence to its mx plus b counterpart, and then also to work with the idea of an explicit rule, which is a new way to write our rule in a more efficient way when we want to run out way in the sequence and get there real quick.